Okay, so welcome to today's lesson. We are going through questions on chemical equilibrium. Okay, and the first question is this question that you are seeing on your screen here. Okay, so here the question says the following results were collected for two experiments involving the reaction at 600 degrees Celsius between gaseous sulfur dioxide and oxygen to form what? Sulfur trioxide. Okay, so meaning that you have your sulfur dioxide here plus the oxygen, okay, and this is reacting to form sulfur trioxide. So sulfur trioxide, it means you have a 3 down there. Okay, so this is the reaction that is happening. So they conducted two experiments. Okay, the first one was this, and then the other one was this guy here. Okay, and then we have concentrations here. Okay, so we have initial concentrations and then equilibrium concentrations. Even for the experiment 2, we also have initial concentrations and then equilibrium concentrations. Okay, so now the question is, they're saying show that the equilibrium constant is the same in both cases. Okay, so you have to know that for you to find the equilibrium constant, okay, then you have to know the concentrations at equilibrium. Okay, you can't use these ones here, the initial concentrations, to find the equilibrium constant. Okay, you always use the concentrations at equilibrium, like these ones and these ones here. Okay, so how do you calculate this equilibrium constant? Okay, so you say K is equals to, okay, and then you get the concentration of all the products that you have. So in this case, we only have one product, okay, we only have one product. So it means this guy here is going to be on top, and then you raise it to the power, okay, to the power, the coefficient moles that you are going to have once you balance this reaction here, okay, and then you divide by the reactants, and then you also raise them to the coefficient of the moles that they have in front here. Okay, so the first thing here, in fact, is always to balance the what? This reaction here. So let's balance this reaction. Let me go to my cupboard here somewhere. Okay, so the reaction was sulfur dioxide, and then we are reacting this with oxygen, okay, to form what? Sulfur trioxide. So the first thing here is to balance this reaction. So how do we balance this reaction? Okay, it's very easy to balance this reaction. Just put a 2 here and you add another 2 here. Okay, so you see that you have 2 sulfur, and then from here you have 6 oxygens. Here you have 4 plus these 2, 6. So we have balanced both sides. Okay, and then we said the equilibrium constant. Okay, we are just getting the product, the concentration of the product, which will be SO3. Okay, you raise it to the power, the coefficient of the moles that you have in front there. So this will be raised to the power 2, and then divided by the reactants, the concentration of the reactants. So this sulfur dioxide, it has a 2 in front, so this will be raised to the power 2. And then we are multiplying this by the oxygen. And you see that the oxygen has only a 1 in front of it. So this will just be to the power 1. Or in fact, you cannot write the 1. Okay, so we are going to use this formula to find the equilibrium constant for this guy here and the equilibrium constant for this guy here. Okay, so let's do that. So I'll divide this my cupboard into 2. This one here will be for experiment 1. This one here will be for experiment 2. So let's get the equilibrium concentrations, okay, for the sulfur dioxide, for the oxygen, and for the sulfur trioxide. So for the sulfur dioxide for experiment 1, we had 150. At 150, we had 1.5, okay, 0 molar. And then for the oxygen, we had what? We had 1.25 molar. And then for the sulfur trioxide, okay, its concentration, we were given that it is 3.50 molar. Okay, so we can use these guys here to find the equilibrium constant. In fact, let me just find it right here. Okay, so let's use these concentrations to find the equilibrium constant for experiment 1. So we're going to say K for experiment 1 is just equals to, okay? So remember, we are using this formula, guys. We're using this formula here. So what is the concentration of sulfur trioxide? It is 3.5. And we are raising this to the what? To the power 2. And then dividing all this, okay? We are dividing all this by, we are dividing all this by
So I can't hear you. I don't know if it's just me.
oh, sorry. My mic got muted. Okay. You can hear me right now, right?
Yes, sir.
Okay. So I was saying you just get these concentrations here. For the concentration for here, you put it on top. The concentration of here, you just replace them there. Okay, so you get your calculator, you put 3.5 squared. My calculator, it's saying 12.25. And then I'm dividing all this by the square of this multiplied by 1.25. Okay, so according to my calculator, it's giving me a 2.8125. Okay, so please counter check these answers with your own calculator. And if I divide this, it's giving me 4.3556. Okay, so this is the first K that I've found. Okay, I've found this as my first K. Then let's calculate the second K now. Okay, so second K, we're going to put the concentration of the sulfur trioxide, which is this guy here. So 0.260 to the power 2 is 0.260 to the power 2. Then we're dividing all this by the concentration of the sulfur dioxide. In this case, it is 0.500. So this is to the power 2, and then we're multiplying by the concentration of the oxygen, which was, this one here should be 0.59, yeah. And then here, it's 0.045 for the oxygen. Okay, so this is what we have here. Then you punch this value into your calculator. On top, when I punch this, I'm getting 0.0676 divided by, when I multiply this down here on my calculator, I'm getting 0.01, 0.01, 56645. Okay, and then you divide this, I'm getting a 4.35149044. Okay, so remember, this is our K2 now. So that I should have written K2 here. So this is our K2. So you compare now this K2 that we found here and the K2 that we found here. Okay, you can see that the answers are similar, right? This is 4.35. Even this guy here is 4.35 something. Okay, so we have found that our K1 is actually equals to our K2. If you round it to 2 decimal places, to be 4.35. Okay, so that's how you show that. I don't know if you have any questions. Any questions, guys, before I go to the next question? Okay, no question. All right, so I'll go to the next question, which is here. Okay, so this is our next question here. Now, what are they asking here? So in this example, okay, they have given us an arbitrary reaction. Okay, A is reacting with B to form C and D. Okay, and they have said we have two of the D's, one of the C's, one of the B, and one of the E. Okay, and then here, this is the most important part here. The energy that they will show here, it will help you answer all these questions here. Okay, so here, the change in energy or the delta H is 230 kilojoules per mole. Okay, so when you look at this value here, you can see that it is positive. Okay, so a positive change in energy or a positive delta H, okay, means that this reaction is endothermic. Okay, it's endothermic, meaning that what it gains energy from the environment, right? Or it takes heat from the environment and it uses it in the reaction. Okay, if this guy here is negative, then it will mean that it is what? Exothermic, meaning it is losing what? Energy, or that reaction produces heat. But if it's positive, like the way it is here, okay, it means it gains heat from the what? From the surroundings. Okay, so that now that we know that this reaction here is an endothermic reaction, it will be very easy for us to judge what will be happening, okay, as they are doing whatever they are doing here. Okay, so here, all this concept here is based on what we call as the Chartier's principle. Okay, so the way the Chartier's principle works is that, okay, in a reaction, when something is missing, the reaction will tend to produce that thing. Or if you have a reaction and you add more of something, the reaction will tend to use that more of something that you've added to produce more products. Okay, in short, the reaction always wants to balance itself. Okay, if there's a shortage, it will start producing more. If there's if there's excess, okay, it will make sure that the reaction runs at a faster rate so that those excess reactants or those excess products, okay, they can be converted into either the products or the reactants. Okay, so this is what will be happening here. So they are saying explain what will happen if D is removed from the chemical reaction. Okay, so remember this reaction here is happening at equilibrium, right? Because these symbols here mean that it's equilibrium. Okay, meaning the rate of the production of the products is the same as the rate of the consumption of the what? The reactants. That's what it means. So if this reaction here is balanced, and then you decide to remove D here, what do you think will happen to this reaction? Anyone who has an idea, what do you think will happen to this reaction? It's at equilibrium, it's happening, and then you decide to remove this D. What will happen to the reaction? Come on, guys, what will happen? What will happen? You've learned these things. What do you think will happen when you remove the D there? Okay, so it's like balance. Okay, it's like balance. So if these things they have the same weight, they will be balanced like that. So once you remove D, it means this side here to be lighter, right? Okay, so what will happen to the reaction? It means that this reaction here, okay, on the left-hand side, will start reacting more so that it replaces this D that you've removed. Okay, so in short, we say that the reaction will shift to the right. Okay, remember when it's at equilibrium, it means the rate of the products that are going this side and the rate of the reactant that are going to this side, they are the same. Okay, then once you just remove this, okay, it means they are no longer the same. It means the reaction will shift to the right. So meaning more of the reactants will be reacting so that they produce the what? The D that you've removed. Okay, so if the D is removed, you say chemically, you say that the reaction will shift to the what? To the right. That's the term that you use. Okay. and then you can explain why it moves to the right. Okay, and then see what will happen when the pressure is increased. Okay, so the secret about pressure is that it only affects gaseous what? Gaseous reactant or product. Okay, if a product or a reactant is not a gas, then it won't be affected by pressure. Okay, so how does pressure affect reactions? Okay, so if you either increase or you decrease the pressure, the part that will be affected will be the parts that have lesser molecules. Okay, is it more molecules? Okay, yeah, I'm supposed to say more molecules. Okay, so the ones that have more molecules or the ones that have more moles are the ones that are going to be affected by pressure. So how do you calculate the number of molecules? You look at the coefficients of these reactants that you have. So here there's 1, 1. So it means on the right-hand side here, we have what? 2 moles. And then here we have 1, here we have 2. So here we have what? 3 moles. So pressure, guys, always affects the side that has what? More of the moles, okay, or more of the molecules, okay? So when you increase pressure here, it means this side here, since it has more of the molecules, okay, it will be affected. So it means more reaction will be happening on the left here. So when more reaction is happening on the left, it means more of these reactants have been what? Produced. So when this pressure is increased, the reaction will shift to the right, to the left. This is the left. So the reaction will shift to the left. It will start producing more of the A's and B because this C and D are reacting more frequently. Okay, why? Because they have more of the particles here. So always when they ask you about pressure, just identify the side that has more molecules, okay, and then the reaction will shift to the opposite side of the side that has what? More molecules. That's how you do it for the pressure. Okay, so increasing pressure will always favor the side of the reaction with the fewer moles. Okay, why? Because the ones with the more moles will start reacting a lot. So these ones here will be produced in bulk like that. Okay. All right. So, and then what will happen if we reduce the temperature? Okay. So for you to know what will happen when you either increase or reduce the temperature, it matters with the reaction that you have. Okay. If it's endothermic, then what will happen will be different from what will happen in the what? The endothermic. Okay. All right. So this reaction here, we said it was what? We said this reaction here was endothermic, right? Because it has a positive delta H. So if something has a positive delta H, we take that energy as a reactant, okay? Because it absorbs energy. That reaction absorbs energy. It means for it to happen, okay, you need more energy. So this energy here, in an endothermic reaction, it is considered as a reactant, okay? So you can add here, you add your delta H here as a reactant, okay? So when this temperature is reduced here, it means we are removing heat, right? When you reduce the temperature, you reduce the heat. So if the temperature is reduced, it means I'm reducing this reactant here. So if I'm reducing the amount of reactants that I have, what will happen? Okay, it means the equilibrium there will shift to the left. So this C and this 2D here will start reacting more so that they replace this temperature that has been what? Lowered, or that has been what? Reduced. Okay, so here on number 3 here, you say that the temperature, the reaction will shift to the left. Why? Because the temperature has been reduced and we are dealing with an endothermic reaction. Okay, so it's the same as you've removed some reactant. So meaning the products now will start reacting more to produce those reactants that are what? That have been reduced. Okay, so any questions there, guys? Okay, no question. I'll go to the next question. Okay, so this is the next question here. Very good question. They are saying what now? So we are also using the Chatrias principle here. Okay. So they're saying if we eject some water molecules, what will happen to the forward reaction? Okay, so this one here on your left is the forward reaction, and then the one on the right there is the reverse reaction. Okay, so the forward reaction produces the products, the reverse reaction produces the what? The reactants. Okay, so if this reaction here is occurring at equilibrium, right? Okay, and then you decide to add more of the oxygen here, what will happen to the forward reaction? Okay, it means the forward reaction there will increase because here we have more reactants now. So you add more of these molecules like that. Okay, so if you add more of these molecules here, it means what? It means this forward reaction here will increase because it has more particles to collide, more particles to react with. Okay, so the forward reaction there will increase. So that is according to Le Chatrias principle. Okay, so you can say the system will respond by shifting the equilibrium to the right, favoring the forward reaction. Okay, this shift will increase the production of this oxygen that we can see. I mean, this hydrogen that we can see here, and this carbon dioxide that we can see there. Okay, to reduce the amount of water that is what being added. Okay, and as a result, they are re-establishing what? The equilibrium. Okay, so that's all about chemical equilibrium. It's just about getting back to the balanced state. Okay, and what do reactions do to get back to the balanced state? It's either they will shift to the right, shift to the left, depending on the conditions that you've been exposed to. Okay, so here if you add more water, this forward reaction will increase and more products will be produced. Okay, so any questions there?
Excuse me, sir.
Yes.
You have said so the reaction here when we add more water to the left, so that means the reaction will shift to the right or to the left.
The reaction will shift to the right because the forward reaction will increase.
Also, for it to balance, that to shift to the right.
Yes, because you are adding more water here, right? So you want to balance that water. So it means the water will be reacting more with this carbon dioxide so that it reduces in the amount.
All right, sir.
All right. Okay, so the next question now is this question here where we are asked to calculate the K and look at some of the properties of the equilibrium constant. Okay, so it has specific properties depending on what you do to the overall reaction. Okay, so if you multiply the whole reaction by a constant, what happens to the equilibrium constant? That's what we want to find out. If you reverse the reaction, what happens to the equilibrium constant? Okay, so these are very important two properties that I'm going to discuss here. So pay attention. Okay, so here they're saying the following equilibrium concentrations were observed for the Haber process of the synthesis of ammonia at 127 degrees Celsius. So here, these are the concentrations, okay? The concentrations in moles of ammonia, nitrogen, and hydrogen, okay? And then they are saying calculate the value of K at this temperature for this reaction, okay? So we know how to calculate the value of K, but the first thing here that we have to do is write the balanced chemical equation for the production of what? Ammonia. Okay, so let's write the balanced chemical equation here. So we know that ammonia is just a combination of the nitrogen plus the hydrogen. Okay, and we know that this produces what? Produces NH3, which is the ammonia that we want. Okay, so don't forget to balance your reaction. Don't forget to balance your reaction. So you balance this by putting a 3 here and a 2 here. So this is balanced now. Okay. And then we are calculating the what? The K. So K is equals to the concentration of this guy to the power 2, because yeah, it has a 2 in front, divided by the concentration of this to the power 3 because it has a 3, multiplied by the concentration of this to the power 1 because it has 1 in front, like that. Okay, so I'm going to say the concentration of ammonia was 3.1 multiplied by 10 to the power minus 2 squared. And then I'm dividing all this by the concentration of this multiplied to the power 3. Okay, what was the concentration of hydrogen there? Forgotten the value. 8.5, this 3.1. Okay, so let's put the 8.5 here. 8.5 multiplied by 10 to the power 1. Okay, and then for the, okay, so this one here should be to the power 3, right? Which one should be to the power 3? Let me check. Okay, so the hydrogen, this one here should be to the power 3, and then this one. Okay, so this one here is to the power 1, and then the 3.1 multiplied by 10 to the power minus 3 to the power what? 3. So this is what we have. So here is just the issue of you getting your calculator and then you punch these values. Okay, so when you punch the value on top there, what are you going to get? I'm getting on my calculator 9.61 multiplied by 10 to the power minus 4. This is what I'm getting. And then I'm dividing all this by, if I punch this into the calculator, it's still the same. It's 8.5 multiplied by 10 to the power minus 1. Okay, and then the other one here, if I punch it and I put it to the power 3, it's giving me 3, it's giving me 2.999. I'll just write it as 3.0 multiplied by 10 to the power minus 8. Okay, so this is what I have here. And then let me now punch this into the calculator, the whole thing. Okay, so when I punch the whole thing, I'm getting approximately 3.77 multiplied by 10 to the power what? 4. Yes, I'm getting this as my equilibrium constant, like that. So this is what I'm getting. Okay, so it means we've answered the first question here, which is calculate this. And then B here, they're saying calculate the value of the equilibrium constant for the reaction. So you realize that here now they have just reversed the reaction. Remember, this nitrogen and hydrogen, they were reactants, but here they are products now. Okay, so that's a very important property of the equilibrium constant. So how do you find that? Okay, so we say that the equilibrium constant for the reverse reaction indicated by K prime is just equals to 1 divided by the equilibrium constant for the forward reaction. Okay, so to find this, we're just going to say 1 divided by the value of K, which is this guy here. So 3.77 multiplied by 10 to the power 4. So whatever we find here will be the equilibrium constant for the reverse reaction. Okay, so let me punch this into my calculator. Okay, when I punch it into my calculator, I'm getting 2.6525 multiplied by 10 to the power minus 5. You can put this to 3 significant figures. 6.5 multiplied by 10 to the power minus 5. Okay, so this is the equilibrium constant for the reverse reaction. Okay, for the reverse reaction is this. So remember this formula here. Don't forget this formula for the reverse reaction. Okay, but if you want, you can find this K prime by again using this same formula here. But since now the nitrogen and the hydrogen are products, it means whatever is in the denominator here will be on top, and whatever is in the numerator will be in the denominator, right? When you divide, you still get this value here. Okay, but this one here is a shorter way. So always use this shorter way. Okay, let's look at another property now when the reaction has been multiplied by a constant. So look at this reaction here. Okay, look at this reaction here. So this reaction here, it has just been multiplied by half throughout. Okay, the forward reaction, the way it was, then we have been multiplied by half throughout. So you can see that here there was a 2, but because we've been multiplied by half, it has disappeared. So it was like this. I think let me show it. Okay, it was like n squared plus 3H2. And then we had 2 of the ammonia like that, right? So all this here has been multiplied by half. Okay, so you have multiplied by half everywhere like that. So when you multiply by half, you get what? You get half N2 plus, multiply this 3 by half, you have 3 over 2. H2 is equals to half multiplied by 2. The 2 will disappear, right? You just have this. Okay, and the question now is to find the equilibrium constant for this. So how do you find the equilibrium constant for such? Okay, so again, you use the special relationship. Okay, so the equilibrium constant indicated by K prime prime, meaning you've multiplied by a constant, okay, is just equals to the equilibrium constant for the original reaction to the power n. So this n here is the constant that you multiply with throughout here. So in this case, our n is what? Is half. So we are going to put half where there's n there. Because we have multiplied all this reaction here by half. So we are going to put half here. Okay, and then this will be equals to, so you put your value of K 3.77 multiplied by 10 to the power 4, and then you raise this to the power half. Okay, so just punch this into your calculator to get your K prime prime. This will be, okay, so I'm getting a 194.2 as the equilibrium constant when I multiply the reaction by a half. Okay. Any questions there, guys? Any questions there? Okay, no question. I'll move to the next question, which is this one here. Okay, so here it's just the English they're trying to play with. But as long as you understand what they're saying, you'll be able to find whatever they want, okay? So here they're saying, assume that the reaction for the formation of gaseous hydrogen fluoride from hydrogen and fluorine has an equilibrium constant of this. So in this question, we've been given the equilibrium constant, okay? And then they're saying in a particular experiment, 3.00 moles of each component were added, okay, to a 1.5 liter flask, okay? So 3.00 moles of each component. So meaning which component? The hydrogen fluoride, the hydrogen, and the fluoride. Each of these had 3 moles, and then they were added to a 1.5 liter flask, okay? And then the question now is calculate the equilibrium concentrations for all the species. Okay, so this is a situation where we use the ice table. Okay, we use the ice table. So the ice table simply stands for initial, the change, and the equilibrium. So we call it the ice table. So we can draw the ice table for whatever we have here. Okay, so but first, before we draw the ice table, we have to calculate the concentration of the hydrogen fluoride, the hydrogen, and the fluorine. So from the topic moles, we know that the concentration is equals to what? Moles over the volume. So the moles we've been given, each of them is 3 moles, and they are put in a 1.5 liter container. Okay, so this is what we are going to use to find the moles. So let's find the moles, I mean the concentration for all those 3. So the concentration of hydrogen will be equals to, okay, the moles, which is 3 divided by the volume. So this will just be what? 2.0 what molar. And then we calculate the moles of the fluorine. So moles of the fluorine will still be the same because it's 3 divided by 1.5. Okay, so all of them will just be 2.0 molar. So this will be 2.0 molar. And then the other one now is hydrogen what? Fluoride. So hydrogen fluoride, we also have 3 moles of it dissolved in a 1.5 watt container. So we have 2.0 watt molar. So these concentrations that we found here, they are our initial what? Concentrations. Okay, so now for us to draw the ice table, it means we have to come up with a balanced chemical equation for the hydrogen, the fluoride, and the hydrogen fluoride here. Okay, so the balanced chemical equation is hydrogen plus fluorine. That should be 2, not E. Okay, so the fluorine, this will give you what? Hydrogen fluoride. So how do you balance this? You simply add a 2 here. Okay, so based on this reaction here, we are going to come up with what? The ice table. So the ice table, we are going to say the initial, the change, and then the equilibrium here. Okay, so this is the ice table. Okay, so what is the initial concentration of the hydrogen? It is just 2.0. What is the initial of this guy? It is just 2.0. And then what is the initial for this guy here? It's also what? 2.0. All right, and then what is the change? So the change, depending on what, either it's a product or a reactant, okay? If it's a reactant, you get minus x of the coefficient that you have in front here. So the coefficient that I have here is 1. The coefficient that I have here is 1. The coefficient that I have here is 2. Okay. So because these two here are reactant, it means their concentration is reducing, right? So it's reducing by what? Minus x. Even this one here will reduce by minus x. Okay. And then the hydrogen fluoride here will increase by what? A positive 2x. Because it's a product, so it's been formed. So it will increase by 2 by x multiplied by the coefficient that is in front here, which is 2. Okay, so this is the change here. And then from here, we can get the equilibrium concentration. So it means the equilibrium concentration here will just be 2 minus x. Even here, it will be 2 minus x. And then there, it will be what? 2 plus 2x. Okay, so remember I said when you're finding the equilibrium constant, okay, you always use the concentrations at equilibrium. So we found the concentrations at equilibrium in terms of x. Okay, we found the concentration of equilibrium in terms of the x. And then we can use the value of the equilibrium constant to find that value of x. So this is the value of the equilibrium constant. So remember the equilibrium constant, which is this. Okay, so I was saying the value of the equilibrium constant is this guy here, 1.15 multiplied by 10 to the power 2. So you're going to say 1.15 multiplied by 10 to the power 2 is equals to, okay? And then you put the products on top here. So the concentration of hydrogen fluoride, which is what? 2 plus 2x. And this should be raised to the power 2 because in its formula here, we have a 2, okay? And then down there, we're going to put those 2. So down here, we're going to put 2 minus x. And then again, 2 minus x. So all these here to the power 1 to the power 1, because the coefficient there is 1, right? Okay, so you end up with that equation there, which you can turn into a quadratic equation. Okay, you can turn it into a quadratic equation. Okay, so here we see that we can have 1.15 multiplied by 10 to the power 2, which is equals to 2 plus 2x to the power 2 divided by, okay? So these things here are the same, you can see, right? So it's the same as I write 2 minus x to the power 2, like this. They are the same, okay? And then now let's take square roots on both sides. So if you take a square root on this side, what are you going to have? So if I take a square root on this side and a square root of the thing that is on top, okay? And the square root of this guy that is on top, right? That is on the bottom here. So here we are going to remain with the value of the square root of this. So punch this into your calculator. So you do square root and then you put this value into the brackets, okay? So if you do that, you're going to get 10.732 approximately. And then here, if I introduce this root here, it's going to cancel with this 2. Even this root down here is going to cancel with this 2. So it means I have 2 plus 2x divided by 2 minus what? 2x. And then from here, I can do my cross multiplication. Okay, can do my cross multiplication. So I'm going to say this guy here multiplied by this. What am I getting? Okay, so 10 multiplied by this. My calculator is saying I'm getting a 21.4, 4, and then 6, and then 10.723 multiplied by x. I'm getting the same number with x. Okay, and then on the other side, I have 2 plus 2x. Okay, so let's put the like terms together here. Okay, let's put the like terms together. So this guy here, let's leave him here. So let's say 21.446 minus 2. So this minus 2, I've gotten this guy, it has come this side, right? Is equals to 2x plus 10.723x. So this is what I have here. Okay, let's subtract this. My calculator is saying 19.446 is equals to, then here we add, I'm getting a 12.723x. Okay, so remember we want to find our x, right? So you divide both sides by this 12.723. Even this side, you divide by 12.723. Okay, so this will cancel. It means our x will just be equals to this guy here. Punch it into your calculator. So what did it give me? Okay, so it's giving me approximately 1.528. So this is what I get here. Okay, so this is the value of x that I've gotten. So remember, our concentrations at equilibrium were these guys here. Were this, and this. So to find these concentrations at equilibrium, we're just going to say 2 minus that x that we found here. Again, 2 minus that x we found. Then here we're going to say 2 plus 2 of the x that we found. Okay, so let's find it. So we are going to say the equilibrium concentration of this hydrogen will just be 2.0 minus the x that we are from finding, which is 1.528. This will give me 0.472 molar as the concentration at equilibrium for the hydrogen. And then for the fluorine, it's going to be the same as this. So it's just 2 minus 1.528 is equals to, it will be the same value here, molar. And then for the hydrogen fluoride, okay, for the hydrogen fluoride, it will be what? It will be 2 plus 2 of the 1.528. Okay, what is this giving me? I will punch it on my calculator. Okay, it's giving me 5.056 molar. Okay, so these here, guys, are my concentrations at equilibrium from that question there. I don't know if there are any questions there you are free to ask. Okay, no questions. Okay, let's solve the other questions. The other question, I think this is the last one on the questions that I was sent. Yeah, I think, yeah, this is the last one here. Okay, so let's solve it. So it's similar to the other questions that we solved. So they are saying the following equilibrium pressures. Okay, so it's very important again to note that you can also find the equilibrium constant when you are given pressures and not the concentration. Okay, but the method to use is just the same. And then you can also convert your equilibrium concentration from that of pressures to that of moles, or to that of concentration, or from that of concentration to that of what pressures. You can counter convert them or change them. Okay, so here they're saying the following equilibrium pressures were observed at a certain temperature for the reaction. So this is just the Haber process. Okay, we are manufacturing ammonia. So the pressure for the ammonia is this guy. The pressure for the nitrogen is this guy. The pressure for the hydrogen is this guy. Then they're saying calculate the value of the equilibrium constant Kp. Okay. So if you are given the pressures, it means your equilibrium constant will be in terms of the pressures, right? So we write as Kp. But how we find it is the same. So we are going to say NH3 here to the power 2, this product divided by N2, and then H2 to the power what? This is H2 to the power 3. So we're going to use this formula here. So let's solve it on my board here. Okay, let's solve it here. All right, so we are going to say our Kp will just be equals to, okay, 3.1 multiplied by 10 to the power minus 2. And this value is the same there with the other question that we solved. I think they are the same, so we're going to get the same value. So 8.5 multiplied minus 1, and then we are multiplying this by 3.1 multiplied by 10 to the power minus 3 squared, like that. Okay, so when you punch this into the calculator, you should get the 3.77 multiplied by 10 to the power what? 4. Okay, so this is the equilibrium constant in terms of the pressures. And then let's look at the other question. The other question now, they are saying if K, okay, for this reaction is this guy here at 400 kelvins, what is the equilibrium constant Kp at the same pressure? So we are converting from an equilibrium concentration in terms of, an equilibrium constant in terms of concentration to an equilibrium constant in terms of what? Pressure. Okay, so there is a formula that we have to know. We just have to know the formula, then we are good to. So we use this formula to convert, okay, from one to the other. So Kp is equals to, okay, Kc. This Kc is the one that they write as K. So when you just see K, it's the same as Kc, meaning the equilibrium constant in terms of the concentration, okay? And then you multiply with RT. So R is the gas constant, T is the temperature, and then you raise this guy here to the power delta N. So this delta N is just the change in moles between the product side and the reactant side. Okay, so how do you get that change in moles? So change in moles, you look at the molecules on your left and the molecules on your what? On your right. So here, the molecules on my right here, we just have 2. Okay, so it will be 2 minus, then the molecules here, I have 1 here plus 3, so I have 4. So the change in moles will just be what? Minus 2. So our change or our delta N here will be what? -2. And then the temperature, we were told it's what? It's 400 kelvins. So always change the temperature that you've been given to kelvins. In case they give you in degrees, change it to Kelvin. And then that R we are given here. Okay, the R we are given, this is the R here. So we're just going to get it and use it. Okay, so the R there will just be 0.08314. Okay, so this is what I need in order for me to convert. And then the KC, I should also know it. So the KC, we were given that it is 4.5, I mean, multiplied by 10 to the power what? 4. So let's just input these into this formula for us to find the KP. Okay, so we're going to say KP is equals to the KC multiplied by 10 to the power 4. And then we are multiplying this by 0.08314 multiplied by the temperature, which is 400. Okay, and then we are raising this to the power change in N, which is minus what? 2. Okay, so what remains here is just to simplify this on your calculator. Okay, so I'm going to have, let me keep this constant first, and then I multiply those two in the brackets. Okay, so when I multiply these here on my calculator, I'm getting 33.256 to the power minus 2. Okay, so this is equals to, when you multiply this on your calculator, what are you going to get? Okay, so my calculator here, it's giving me the final answer is 40.6885799. So make sure you counter check these answers. So my KP, if I was to round it off to 3 significant figures, would just be 4.7, 40.7, I mean. Okay, so this is what I have there. So any questions from there? Okay, any questions, guys? I think that was the last question. Okay, so I'll end here if there are no questions. You can watch tutorial sheet 8, it's there on Drive, even the written solutions. Tutorial sheet 9, it's also there with the video and the written solutions. Tutorial sheet 10 is also there. Okay, so choose your best. So have a blessed night.